So, hello everyone. In this video, I wanted to make another exercise related to how you can compute the Thevenin equivalent for this circuit. Okay. In this case, the problem is asking us to compute the Thevenin equivalent between terminals A and B. Okay, that is in this part of the circuit. So remember that we need to solve the circuit by using two main approaches. First, we need to compute the voltage between terminals B and A and B, that is equal to the Thevenin voltage. Okay, so how can we compute that Thevenin voltage for this circuit? Well, in this case, you can observe that here we have one node, okay, and also we have um, well, instead of solving this by using nodes, maybe we can use meshes. Okay. So for example, here we have one mesh. Okay. And here we have another mesh. Okay. And in this mesh number one, we have a current I1 that is flowing through this through this loop. Okay. And for mesh number two, we have a current I2 that is flowing through this second mesh. Okay. In fact, you can notice that I1 is equal to 4 with an angle of 0 degrees amperes. Okay? And that means that, well, these two currents are equal because you can notice that here we have this voltage source that is pointing in the same direction to I1. Okay, so that is why we are making we are making this expression, no? That I1 is equal to the value of the current source. Okay? And for mesh number two, okay, you can notice that, well, here we have the current I2, okay, and we can apply the Kirchhoff voltage law to this loop, okay? So you need to be very careful about the direction of the current. So for example, here you can see that the current I2 is flowing through this capacitor, okay? This capacitor right here. So we can compute the voltage drop into that capacitor by considering that I2 is multiplied by the impedance value, that is minus J 5 ohms. Okay, this is the voltage drop in this element. And also you can notice that I2 will be flowing through the inductor, okay, through this value, okay? And we have no current flow in this direction because well, there is an open circuit, okay, pointing in this direction. So that's why we can say that the current I2 will be flowing only through the inductor. So we can say that the voltage drop in this element is I2 multiplied by J times 10 ohms. Okay, and now we need to compute the current that is flowing through the 8 ohm resistor. Okay, so we can compute that as follows. We will place a positive sign, and then you can see that we have here the 8 ohm resistor, but we need to compute the current that is flowing through this element. So here you can see that, well, the current that is flowing through this element will be the difference in currents between the resistor, between I2 or the current that is flowing through mesh number two and minus the current that is flowing through mesh number one. Okay, so that basically means that, well, the current that is flowing through this resistor is the difference in currents between mesh number two and mesh number one. Okay, and with this difference in currents, we can compute the voltage drop in this element, and this should be equal to 0 according to the Kirchhoff voltage law. So if you in this case, you can set up a system of two equations and two incognitas. Here we have one equation, and here we have the second equation. Okay, in fact, you can substitute I1 in this equation, and you can solve for I2. So I2 is equal to 3.3919, okay, with an angle of minus 32.005 degrees, and these are amperes. Okay, so this is the value of the current I2. Okay, um, but now remember that we need to compute the voltage between the terminals A and B, that is equal to the Thevenin voltage. But you can notice that the voltage, this voltage between terminals A and B is equal to the voltage of this inductor, okay, that has an impedance of J 10 ohms. And we can say that, well, the voltage in this inductor with an impedance of J 10 ohms is equal to I2, okay, times the impedance value, that is J times 10 ohms, okay, and this is equal to, mm, well, 33.9119 with an angle of 57.99 46 degrees, and these are volts. Okay, so this is the voltage. Okay, for this inductor that is equal to the Thevenin voltage. Okay, this is the Thevenin voltage. Now, we now need to compute the equivalent impedance that is seen between terminals A and B. So in order to compute the equivalent impedance of the circuit, we need to turn off all of the sources in the circuit. So we only have one source right here, that is this current source, and I need to turn off this element. So since we have here a current source, we can model that this current source is off by making an open circuit. Okay, and the reason for that is that since you have here a current that is flowing, okay, you have a current source, we can say that if we turn off this current source, that means that we have a very high resistance. And we can represent this very high resistance by placing an open circuit, because in an open circuit, there is no current flow. So we can place the terminals right here. Okay. Here we have the 10 ohm, the 8 ohm resistor. Then here we have this capacitor. And here we have its impedance of this capacitor. And here we have the inductor. Okay, and the inductor has this impedance. And we have here the terminals. Okay, A and B. And here I place the open circuit for showing that the current source is off. But how can we simplify or compute the equivalent impedance? Well, as a matter of fact, these terminals doesn't are making anything to the circuit. No, we can erase them because there is no current flow, there is no voltage drop, because there is nothing there. No, so we can write the circuit in this way, and you will notice that these two components are in series. Okay, so you can add these impedances together, and you will notice, or if you look very closely into the circuit, you will notice that the equivalent impedance between these two elements is in parallel with this inductor. And the reason for that is that the equivalent impedance by adding this 8 ohm resistor with with the impedance of the capacitor are in parallel with the inductor. Okay, so well, I am writing here this parallel expression, and if you compute the parallel of that, you will obtain the following result, that is 10 with an angle of 25.98 and 92 degrees ohms. Okay, this is the equivalent impedance, or the equivalent Thevenin impedance, that is equal to the Norton impedance. Okay, so remember that the Thevenin equivalent can be expressed as a voltage source, okay, in series with impedance element. Okay, and here we have the equivalent circuit. This is the Thevenin equivalent. Also, we can generate an Norton equivalent, okay, by placing a current source, okay, in parallel with the impedance, okay, with the Norton impedance. that is equal to the Thevenin impedance. Okay, and here we have some terminals. And how can you compute this Norton impedance? Sorry, this Norton current. Well, this is equal to the Thevenin voltage divided by the um, Thevenin impedance, that is also equal to the Norton impedance. Okay, so we can substitute these two values in this equation. Okay, and here you will notice that this should be equal to, well, we need to compute to take into account Thevenin voltage, that is 33.9199 with an angle of 57.9946 degrees volts. And this is all divided by the Thevenin impedance, that is 10 with an angle of 25.9892 degrees ohms. So you can say that the Norton current is equal to 3.39 199 with an angle of 32.00536 degrees amperes. Okay, so this is basically the result of this exercise. Here we have the voltage, the Thevenin voltage, the Thevenin impedance, and here we have the Norton impedance. Okay, so that's all for this video. I hope it can be useful to understand this concept of the equivalent circuit obtained through the Thevenin and Norton methodologies. So I will later make some examples into how you can use this concept of the Thevenin and Norton equivalences in order to solve the maximum power transfer. Okay, so see you later.